Ever wondered how we know the temperatures and densities of the sun's core? Picture the sun, a colossal sphere of plasma. At its heart, temperatures skyrocket to over 10 million degrees Celsius and densities reach more than 20 times that of solid iron. Yet, at the surface, these numbers plunge dramatically. These facts alone are astounding. But what's even more mind-boggling is our ability to know them. After all, how can scientists understand the sun's interior when the only light we see comes from its outer layer? You might think it's impossible, like trying to understand the mystery of an unopened book by only looking at its cover. Yet it's not. The key to unlocking this celestial riddle isn't found in some far-off alien technology, but rather in a field of study we've been familiar with for decades. The answer to this seemingly impossible question lies in the fascinating science of helioseismology. Earthquakes, while scary, provide invaluable insight into the Earth's interior. Imagine a pebble thrown into a pond. The ripples that spread outwards are not unlike the waves created by an earthquake. These waves, powerful and far-reaching, give geophysicists a chance to peer into the heart of our planet. When an earthquake strikes, it sends out waves that travel through the Earth, starting from the epicenter and reaching far beyond. These waves, although diminished by the time they reach the surface, can be detected as tiny tremors in places distant from their source. Geophysicists use sophisticated instruments known as seismographs to record these tremors. The data collected is then meticulously analyzed using mathematical physics related to wave propagation. This might seem like a daunting task, but it's all in a day's work for these scientists. The analysis of these waves allows geophysicists to do two remarkable things. First, they can trace the path that the waves took through the Earth. This gives them a roadmap of sorts, charting the journey of the waves from their point of origin to their point of detection. Second, they can work backward from these paths to reconstruct the properties of the Earth's inner layers. It's like having a reverse-engineered blueprint of the Earth's interior, revealing the structure of its innermost layers. This scientific discipline, known as seismology, is a powerful tool that lets us map the internal structure of our planet. It gives us a way to understand what lies beneath the surface in the hidden depths of the Earth. But seismology isn't just useful for studying our planet. Astronomers, in their quest to understand the stars, realized that they could use similar techniques to study the sun. And thus, many decades ago, a revolution in our understanding of stars was launched. This science of seismology has also found its use in understanding our very own star, the sun. In the 1960s, a revolution in our understanding of stars was launched. This was the decade when telescopes began to reveal a peculiar rhythm in the sun's behavior. Every 5 minutes, the surface of the sun would rise and fall in a steady oscillation, a celestial heartbeat in the vacuum of space. But what could possibly cause this? The answer was hidden deep within the sun itself. Scientists observed a distinctive pattern in the light emitted by the sun. As the surface rose, it resulted in a Doppler blue shift, followed by a Doppler red shift as the surface fell. This intriguing discovery suggested that these surface oscillations were not random, but the result of waves propagating inside the sun. Just as earthquakes produce waves that traveled through the Earth's interior, the sun was producing its own seismic waves. This was a moment of profound realization. If these waves could be tracked and analyzed, just like seismic waves on Earth, then they could provide a window into the inner workings of the sun. This was the birth of helioseismology, a revolutionary new field of study that combined the principles of seismology with astrophysics. Helioseismology allowed solar physicists to do what was previously thought impossible, to map the interior of the sun. By studying the propagation of waves within the sun, they could gain insights into its internal structure and composition, much like geophysicists studying the Earth's interior. This was a game changer, opening up a whole new world of understanding about our closest star, But it's important to remember that helioseismology is not a simple science. It requires the constant monitoring of the sun's surface oscillations. These oscillations, although they cycle every 5 minutes, need to be observed without breaks and over the entire surface simultaneously. This poses a unique set of challenges. On Earth, our telescopes are bound by a 24-hour rotational cycle, making continuous observation difficult. However, helioseismology comes with its own unique challenges and demands. Despite these hurdles, the rewards of helioseismology are immense. It's a testament to our never-ending quest for knowledge, a testament to the power of science to illuminate the mysteries of the universe. Monitoring the sun's surface continuously is no easy task. The pursuit of helioseismology is like a game of chess where the rules keep changing. It requires a careful, continuous observation of the sun's surface, a task that is easier said than done. Firstly, the sun's oscillation cycle within a period of 5 minutes. To capture this, scientists must maintain a vigilant, unbroken watch over the solar surface. Any gaps in observation could result in missing essential data and disrupt the overall analysis. Secondly, the Earth, with its bound